Hello, I am Christian Malaga, and this video will discuss the free vibrations of damped single degree of freedom systems. The key concept here is to understand how the linear viscous damping term influences the solution to the equation of motion of a system without any external action. To this end, we will examine the motion of this translating mass m, representing a single degree of freedom system attached to a spring of stiffness K and a dashpot with a damping coefficient C, but with the external force set equal to 0. Therefore, the equation defining the motion of the system is mass times acceleration plus c times velocity plus k times displacement, all that equal to 0, where c is the damping coefficient and k the stiffness. We are only going to solve this equation by means of complex exponential functions. In order to do so, we postulate a solution for the displacement u, equal to e elevated to lambda t, where t is time and lambda can take complex values. Differentiating it once with respect to time, we obtain the velocity, and differentiating it twice, we arrive to the acceleration. Substituting u dot, and u double dot into the equation of motion yields the following expression. In this case, we are using the dot notation for differentiation with respect to time. We realize that the left-hand side of this equation is the product of the exponential function, whose shape is well known, and the term inside the parentheses, which is lambda squared times m plus lambda times c plus k. In order to ensure that the previous equality is respected, we must equate this bracketed part of this equation to 0. This leads to this quadratic equation. Hence, solving this in the usual way, we arrive to this expression for the roots of lambda, which give two solutions to our problem. Let's take a moment now to define the critical damping. Starting from the previously found expression for the roots of our solution, let's focus on the term inside the radical. Defining the special case where this radical is equal to 0 and solving for c, we arrive to c equal to 2 times the square root of the product of the stiffness and the mass. We call this c sub cr, or critical damping coefficient. Moreover, for any damped system, we define a damping ratio c as the ratio between the damping constant c and the critical damping coefficient c sub cr. This damping ratio will play a key role in defining the motion of our structural system. More generally, we can distinguish three different cases of damped motion. Case 1, when the damping ratio is less than 1 and we say that the system is underdamped. Case 2, when the damping ratio is equal to 1 and the system is critically damped. And case 3, when the damping ratio is less than 1 and the system is overdamped. These last two cases are not of concern to the structural engineer, as in most civil engineering structures, we normally rely on just the inherent damping properties of the system, and damping ratios of less than 5% are the norm. Even in those cases where supplemental damping devices are provided, the damping ratio seldomly exceeds the 20% of the critical value. Going back to the solution to the equation of motion for a damped system undergoing free vibrations, we can recast the previously found expression for the complex exponent lambda as a function of the damping ratio c and the natural circular frequency of the system omega sub n. We note that the frequency of vibration omega sub n on the second term of this equation is scaled by multiplying it with the square root of 1 minus c squared. This scaled version of the frequency is called damped circular frequency, and it is represented by the symbol omega sub d. Therefore, knowing the expressions for lambda and omega sub d, we can state the complete solution to the ODE as the combination of the two roots previously found, one with a positive and another with a negative sign. Finally, we can rearrange this equation to find the following expression, which is composed by a harmonic part and an exponential part that modulates the harmonic motion. As usual, the amplitude of the cosine and sine terms are determined from the initial conditions of displacement u0 and velocity v0 times 0. It is straightforward to confirm that this solution becomes identical to the undamped one when the damping ratio C is set to 0. Plotting the response history of an undamped system with a critical damping ratio of 5% in blue against the background of its corresponding undamped response for the same set of initial conditions in gray, two key observations can be made. First, that energy is taken out of the system, causing an exponential decay in the amplitude of its motion. And second, that the frequency of the vibration is reduced only slightly. These will have important implications for the solution of many dynamic problems.